First of these 4 trends we're going to talk about is atomic radius. Okay, so you'll need the definition somewhere. Okay, and what the atomic radius means, it's half the distance between the nuclei of identical atoms that are bonded together. Okay, so in a very primitive drawing here, let's say that I have 2 hydrogen atoms. Right, here's another hydrogen atom that's bonded together. That means the distance from nuclei to nuclei would be this distance right here. So that means the atomic radius would be that distance, right? We're half the distance between 2 nuclei that are bonded together. Okay, again, that's a very primitive drawing, but we're looking at essentially the distance from the nucleus to the outermost point of an atom. Okay, so in order for us to correctly depict that and to really think about how much that space is or what that distance is, we got to look at 2 atoms that are bonded together, and then we'll take half of that distance from nuclei to nuclei. Okay, the reason it's hard for us to just look at the radius of a single atom is that electrons are so mobile along the outside, right, in that outer shell. It's hard for us to really figure out where they are or how far from the nucleus they are. So we look at 2 of them bonded together. Okay, so would it work to find the atomic radius if we have a hydrogen atom and an oxygen atom? It wouldn't be helpful for us to find the atomic radius because those 2 things have different electronegativity levels. They have different number of valence electrons. They have different shells. Everything is different about that, so it wouldn't work. We got to use 2 of the same. Okay, so the atomic radius trends. What I'm going to give you for all of your trends is I'm going to show you where does it increase to. So we're not always going to work left to right. We're not always going to work bottom to top or whatever. I'm going to show you where does it increase. Okay, so we see an increase in atomic radius when we go from right to left. Okay, so let me pull up a periodic table here. Okay, we see an increase in our atomic radii as we go from right to left. Okay, so we see an increase as we go this way, and we see an increase as we go down. Okay, so the largest atomic radius, theoretically, would be it increases as we go down. So francium would be one of our largest atomic radii. As we move this way, or even if you think about it backwards, why would the atomic radius be getting smaller as you move this way? Right? The atomic radius is going to decrease as we move to the right. Well, the atomic radius is decreasing. That means they're getting closer together as we move that way, right? It's increasing as we're on the left, and it's decreasing as we're on the right. Why do you think?
They become more electronegative as they move to the
Kind of. Okay, that's in the ballpark. It's okay. You're on the right track. What happens as we move left to right on the periodic table in terms of its protons? We increase the positive charge as we move across the periodic table, right? So as we go from lithium to beryllium, we increase the number of protons. As we keep moving, we increase the number of protons, increase the number of protons. What happens as we increase the positive charge in our nucleus?
The negative charge.
Okay, the negative charge does increase a little bit, but what happens to those electrons? No, they get pulled closer, right? We're talking about a decrease. So if we're looking at it increases atomic radius. So this is large radius, and this is small radius. Okay, so if you need to put that again so you can think about it. Small radius means that as we increase the positive charge in those atoms, they're going to pull those electrons a little tighter to themselves, right? If we have a 1-to-1, they're not pulling them quite as much. If we get 2 protons, they're pulling them a little bit tighter. 3 protons are pulling them a little tighter. Okay, so as we increase that positive charge, we're pulling that radius closer and closer to itself. Yeah. Then why does the radius increase as we go down, right? large, and this is smaller up here. Why would the atomic radius increase as we move down the periodic table? This one is probably easier for us to see.
Just the overall mass and stuff.
Kind of. What happens as we move down a group on the periodic table? What do we add? A new shell of electrons, right? So here we're just literally adding electrons to the outer portion of our atom, which is causing that atom to just be overall bigger. Okay? It has less to do with the charge in it. It has more to do with literally just the space they take up. Okay? So as we move further to the left, we see those neutrons and those protons pull the electrons in tighter, right? The nucleus itself pulls it in tighter. As we move downward, we just see the shells themselves expanding. Okay? So the second one we're going to look at is called ionization energy. Ionization energy. Okay, and what ionization energy means, it's the amount of energy required to remove the outermost electron. Oops. From a neutral atom. So why would it be called the ionization energy? What does ion mean?
Like a charged particle.
That's right. An ion has to be a charged particle. So the reason it's called the ionization energy is it's what's the amount of energy required to make it an ion. Right? That's what we're talking about here. We're going from a neutral atom. We're taking away an electron. So what type of ion would that be? Called what? The cation, right? They're positive. Positive. Electron. Yeah, that's the sign for electron. Okay? So when we remove an electron, it becomes more positively charged, called a cation. Okay? So that's why it's called the ionization energy. We're removing an electron, we're plucking an electron from the outermost shell or subshell, and we're making it a cation. Okay. So can anyone guess here what would which element would have the highest ionization energy? Think about what we know in terms of how things behave on the periodic table. Which do you think would have the highest ionization energy? Which would it be hardest to pull an electron from?
The 18. No.
One specific element.
It'd be hard to take it from hydrogen.
Helium. It's helium. Hydrogen only has one valence electron. It wants to give it up.
How are you
Right?
taking it, bro?
So let's look at why that is the case. Okay, let's look at our trend here. So here's our trend for ionization energy. It increases as we go to the right, and it increases as we go up. Okay? So that means we're pointing right toward helium. Helium has our highest ionization energy.
Wait, so the last play, francium?
That means francium would give up its electron most willingly, right? It requires the least amount of energy to remove that electron. Okay, so here's our reason. And our reasons for increase in ionization energy correlate with our reason for decrease in atomic radius, right? As we increase our positive charges on this side, right, as we increase the number of protons in our nucleus, we're pulling those electrons tighter, okay? And that's the same reason we talked about the decrease in atomic radius. These are pulling them tighter and tighter together, which means they don't want to give them up, right? If this one has only one valence electron, right, what does it want to do? Does it want to get 7 more, or does it want to give up that one?
It wants to give it away.
It wants to give that one up. Same with 2 valence electrons. It wants to give it away, okay? So that's why as we go across the periodic table, we see an increase in ionization energy. Why does it increase as we go from the bottom of the periodic table to the top? Less shells, that's right. That means the electrons are closer to the nucleus. Okay, so since in helium, right, we've got 2 electrons which in the first shell is a full shell, right? 2 electrons, and they're as close to the nucleus as they can possibly be. Helium's not giving them up. Okay, it takes a tremendous amount of energy, which you can see on page 154.
But they care less than the other ones.
Okay, it takes a tremendous amount of energy to pull off an electron from helium. Okay, so our third trend is electron affinity. Okay, and what electron affinity means. It's the energy change that occurs when a neutral atom obtains an electron. Okay, so if I put this in a little bit more plain words, that means it's how likely an atom would be to accept an electron. An electron. Okay, and in more plain words, we're saying how likely would an atom be to take an electron, okay, to accept an electron. Yeah, good, very good. Okay, so if we talk about a group as a whole, which would be the group that's most likely to accept an electron? Group 7 or 17, right? They want to accept that one electron. So why is that the case? Why does group 7 want an electron so badly? They got to get to 8, which is called the almost the octet. Yeah, they want an octet. Okay, they want 8 electrons, which is an octet. This trend is less defined as the other ones, so I'll show you kind of what this one looks like.
So it goes like 7, 6, 5, 8, 4, 3.
No. Okay, this trend means that group 17, they have the highest electron affinities. Okay, group 7 or group 17 has the highest electron affinities. Do you think the noble gases has an electron affinity number associated with it? No, it does not. So they don't really have anything. They have no electron affinity. They're not going to take an electron, right? So there's no amount of energy that's going to change because they're not going to take one, okay? Other than that, we just see an increase as we go across the periodic table, for the most part, with electron affinity, right? They're going to be likely to accept an electron. The transition metals are sometimes a little tricky, okay, because they have different charges. They don't follow exactly the rules like everything else. But for the most part, far and away, we see an electron affinity increase as we move through the periodic table from left to right. So for the most part, we'll see an increase there. Okay, if you look on page 158, if you still have your textbook out, we see a chart of electron affinity versus atomic number. So the electron affinity of all of the noble gases is at what? Do you see the electron affinity of the noble gases? They're all at 0, right? And the group 17s are the ones that are making the big peaks down, right? There's a negative energy change. All those big peaks that you see spiking downward, those are all the group 7s or the group 17s. So those are the big ones in terms of electron affinity, okay? The change, or how likely they are to accept an electron. T. When have we looked at electronegativity in the past? What part was that? Periodic table of ions, okay. Yeah, when we talked about bonds. When we talked about what specific types of bonds? Yeah, covalent. Okay, covalent bonds, and more specifically, ionic bonds, polar covalent bonds. Polar covalent bonds is where we really looked at it. And what happens in a polar covalent bond? Let's bring it back here a little bit.
The most electronegative.
They're shared, but what happens in a polar covalent bond?
The most electronegative gets doesn't give them away.
Yeah, pretty close, right? In a polar covalent bond, they're shared unevenly. Electrons are shared unevenly, which means the most electronegative one's going to pull them closer to themselves. Okay, so let's look at the electronegativity. Electronegativity means, the definition, I don't know if we've necessarily looked at the definition before, the ability of an atom in a compound to attract electrons from another atom in the compound. Okay, on page 161, you'll see a periodic table with the electronegativity values labeled. What is that called? Remember I gave you one of those?
Periodic table of electronegativity.
No. It starts with a P.
Periodic.
No.
Polarity.
No. Don't guess if you don't know. So this is called a Pauling scale, and it's on page 161. It gives all of our atoms, that's right, gives all of our atoms an electronegativity value. Why do you think the noble gases, or some of the noble gases, don't have an electronegativity value assigned to them?
Because we don't know. They don't want to attract.
They don't attract.
They don't attract. They're not going to bond with anything, so they're not going to pull electrons from anything else. Xenon, krypton, and radon will sometimes be part of a chemical compound, which means they could theoretically pull electrons from other atoms. But helium, neon, and argon don't. They don't bond with anything. Okay, so they're not given an electronegativity value assigned to them.